So, if we look at an object thrown near the Earth's surface, we would look something like this. Okay, imagine the Earth's surface like that, and we're throwing an object. Let's imagine that it's thrown at 45 degrees to the horizontal, and we have a force acting on the object. Like that. And here's what I was saying before. You need to see that those force lines are nearly parallel, but not quite. Alright, so remember the Earth is very, very large, so the force lines are nearly parallel, and if they were parallel, then the force would be constant. And so in this course, we're going to consider that it is a uniform field, and we're going to treat the analysis as such. If you were doing more advanced physics, so you were looking at how rockets launch or how ballistic missiles travel or something like that, then you would need to consider the fact that it's not a uniform field. Alright, so the question is, what shape is that motion? So it's moving kind of through the field like that, and we have a force acting downwards. And if we consider the case where there's no air resistance, okay, then we can actually start to look at the motion. Now you might say, well, that's not very realistic because there is air on the Earth, and yes, that is true. It turns out that analysing things with air resistance is quite complex, and we just try and get our heads around this first, and then we add in the more complex factors later, which we will do in this course. We won't do a mathematical treatment of it, but we will do a descriptive treatment. Okay, so what is the shape? Anyone know? Well, if you guessed parabolic, you would be correct. There's something else about this shape though that's curious. Without air resistance, the shape is actually symmetrical. Okay, so it's parabolic and it's symmetrical. And we look at the motion, or we analyse or examine the motion. What we are actually going to do is we're going to look at the motion in horizontal and vertical components or parts. Now, what do I mean by that? Well, if we can just consider this example. Alright, let's imagine I've got a block of wood on a table or something like that, and I'm applying two forces to the block of wood. Okay, force 1 and force 2. Now you can see, if we add those two forces together, where's the block going to move? Well, it's kind of going to be moving upwards, but it's also going to be moving sideways at the same time. So what are we going to get? We're going to get a diagonal motion like that. So we kind of do something similar with projectile motion. We look at one motion which is horizontal, one motion which is vertical, and we actually look at them separately, if you like. We analyse them separately. And by doing that, we can actually kind of get our heads around what's actually happening with the motion. Alright? So, we are going to be looking at horizontal and vertical motion. But what's the difference between the two? So if we're looking at the vertical motion, which is in this direction here, we can see that the force of gravity is going to be acting in that direction. And what do we know about when a force acts on an object? We know that it's going to accelerate. Okay, so there's going to be an acceleration in the downwards direction. Actually, strictly speaking, it's towards the centre of the Earth. Right? There's going to be an acceleration towards the centre of the Earth, and it's going to be in the direction of the field. So that's the vertical motion. However, when we threw the object, we also gave it some motion in the horizontal direction. So we gave it some motion upwards. In this case, it's against the force of gravity, or in the opposite direction to the force of gravity, but we also gave it some motion in the horizontal. And when we combine those two motions, or those two forces, then we get a diagonal motion. So that's this initial motion here. Let's do it in red. That's the initial motion there. So, of course, after you let go of the ball, so you throw on the ball, after you've let it go, there is no longer any force from your hand. There's only one force acting, in fact, and that force is the vertical force. So that vertical force is going to be acting in the opposite direction to the upward motion, this one here, causing the ball to decelerate in the upward direction. So we know that if you throw a ball, it'll go up to a certain point, it's decelerating to that point up to 0, then it will change direction and coming back down again. Alright. What about the horizontal direction? Is there any force acting in the horizontal direction? Well, after you throw the ball, okay, so there's a force from your hand, but that's not the motion we're talking about. We're talking about after you let it go, right? So you throw the ball, and we're looking at the motion after you let it go. So once you let the ball go, there is in fact no force acting in the horizontal direction. We must remember that we're not allowing for air resistance at this point. So there's no air resistance and there's no force acting in the horizontal direction. So if you've got no force, what is the acceleration? 0. Okay. Now, when we're looking at motion, we analyse motion using the equations of motion, which hopefully you remember, but we'll write them up here again. So the equations of motion basically connect the velocity, the acceleration, the displacement, or the distance in a particular direction, and the time of the motion together in 3 equations. So those 3 equations look like this. Okay, so they're the 3 equations of motion. And I really should put my vector symbols on there, shouldn't I? So the velocity is a vector. That's the final velocity. This is the initial velocity, the acceleration, and the time. Time is not a vector, it's a scalar, so we don't need the vector symbol. Delta S is the displacement, initial velocity, and acceleration. And these ones are squared, so we don't need a vector symbol, and the acceleration and the displacement as well. Now, I said that the acceleration was 0, right? So that means that this is 0, this is also 0, and this is also 0. Alright, so all we're left with is in the horizontal direction, the final horizontal velocity is equal to the initial horizontal velocity. Well, that's not saying anything profound, it just means it's moving at a constant velocity. Similarly, down the bottom, horizontal velocity squared is equal to the initial horizontal velocity squared. So that's not really telling us anything. So we're just left with this one equation, that the displacement in the horizontal is equal to the initial horizontal velocity multiplied by the time of flight. Right? So there's your displacement in the horizontal, delta S, and that's equal to the initial horizontal velocity times by the time. Okay. With the vertical, it's a little bit different because the acceleration isn't actually zero.